Okay, solubility, what is it? Someone tell us. Calvin.
Ability to dissolve in water.
Good. So when you see the word solubility, it's about the ability to dissolve. The first time we talked about it is, think back to the lab that we did, where's the precipitation lab, where we had the little sheet, and then you drop two things on it, and then sometimes it would turn a color or something like that. What were we looking for in that lab?
How high it rises up.
Kind of, but
For how,
the precipitant, right? So a precipitant we defined as a substance that did not dissolve.
Yeah.
And we kind of left it there. It's actually a little bit more grayish than like things don't dissolve and things do dissolve. Because solubility is actually an equilibrium process. When you pour a salt of any kind, once again, salt's just the name you call ionic compounds. Okay, so let's draw a cute little picture here. Okay, so here's my beaker. Okay, so if I pour some salt, there's water. Okay, here's clumps of salt. Okay, so if I pour some salt into the water and I keep pouring it and stirring, eventually it will stop dissolving, right? Okay, because there's a point at which you can't dissolve anymore based on how much water's in the cup. Okay, so floating around in the water are the positive and negative ions as it dissolves. The equilibrium side is the fact that these ions are attaching while others are constantly dissolving. So it's an equilibrium, it's not static. So the ones that are technically sitting at the bottom aren't actually just sitting there the whole time, they're trading places with the ones in the solution. So another word, and I can't remember if we introduced it last time or when we first learned this, but when you get to the point where you can't dissolve anymore, we call that solution saturated. So saturated is the point of maximum solubility at temperature and water conditions. Because obviously if I pour more water, can I get more salt to dissolve?
Oblivious.
Yes. Okay. But under those conditions, right, that's the maximum level. Now, so undersaturated, so if you say a solution is undersaturated, it means you can keep dissolving. Now, obviously, the really easy way to check to know if something is saturated or not is pour more in. If it doesn't dissolve, you're saturated. If it keeps dissolving, you're not there yet. Okay? Because in order to have an equilibrium system, you have to have both parts.
Does it have to be saturated for it to be equilibrium at equilibrium?
Yes. Yeah, good connection, Calvin. Yeah, you have to be saturated to be at equilibrium. If you're not saturated, you're not at equilibrium because it's not changing places. So, now, this right here is an example of barium sulfate. Because it's an equilibrium system, it has an equilibrium constant. We call it KSP just to signify that it's for solubility. But it's the same exact setup as all our other Ks. So what is the setup for K? Products over reactants, right? So my products are barium and sulfate ions. So Ba2 plus and SO4 minus. Now I think we're learning this, but keep in mind, you've got to have the charges. Because when something dissolves, it doesn't dissolve into an element, it dissolves into an ion, which is very different. Now, the interesting thing with KSPs is the reactant is always a pure solid. And so you don't put it in the expression. So KSPs are actually never fractions because the reactant is always a solid. So it actually kind of simplifies the equilibrium process because there's less you are looking at.
Are those two like aqueous solutions at all? Like because it.
Yes. Yes, so ions are always considered aqueous.
Okay.
Probably a good thing to label on there, but good clarification. Now this is kind of a side note, but it's kind of a cool thing to recognize. So what did saturated mean again?
Can't dissolve.
You can't dissolve anymore, right? If I poured more in, it would just sit there, okay? Something you can do with temperature is you can create what is known as a supersaturated solution, which means you are forcing the system past what normally would dissolve, okay? So for example, a lot of things can do this with temperature, but one that does it kind of in a cool way, sodium acetate. Okay, so I've measured out here in this beaker 160 grams of sodium acetate. So, good question. So, with this solubility product that we're going to calculate now, the biggest thing you need to recognize is that even though the solid isn't in the KSP expression, you have to have solid for it to be in equilibrium, right? Kind of like what Calvin brought up, you have to be saturated for it to be an equilibrium reaction. Otherwise,
It's not changing.
right, there's nothing to change between, okay? All right, so let's look at a problem here of how we calculate KSP. Now try to relate it to what we've learned in the other units, because it's really just equilibrium again, okay? So the question says, solid silver chromate is added to pure water at 25 degrees Celsius. Some of the solid remains undissolved at the bottom of the flask. The mixture is stirred for several days to ensure that equilibrium is achieved. Okay, so I'm just making sure that I'm at the point where, okay, I've dissolved the most and equilibrium is established. We're able to analyze our solution and find that the silver concentration is this, and we want to know what the KSP is for our sample. Okay, so first thing, what is KSP? Good, and how do I write an equilibrium constant? Products over reactants. So, we probably should write an equation so we can have our products and our reactants. So often with solubility problems, they're not going to give you an equation. You have to write it yourself. But what's happening in this reaction?
You're just going from solid to aqueous solution.
It's just dissolving, right? So we have solid silver chromate dissolving into, now what would it dissolve into?
Just silver.
Silver chromate.
Okay, because silver always has a +1 charge. Okay, for a smiley face, don't say it out loud. Does the 2 that's here belong here or here? Point up if you think it should be a big one. Point down if you think it should be the little one. So where does the 2 belong? Because it's on this side, so we need it somewhere. If you're pointing up, have a smiley face. So why? Why, Andrew?
So the little 2 means that those 2 elements are bonding together. So like H2 is just 2 hydrogens that are bonded together. But 2 silver means that there's 2 separate that aren't bonded together, but they're in there.
And when something dissolves, it dissolves as it breaks up all the bonding, right? Well, all the ionic bonding, I should say. So the covalent bond of this stays together, but the 2 silver should separate. Once again, it's a small thing, but it's a big difference in chemistry. Small numbers versus big numbers mean very different things. Okay, so we have our expression, or our equation, so let's plug it over here. So we have Ag plus squared CrO4 2 minus. So to find our equilibrium constant, we need to know the values of these 2 things at equilibrium. What does the problem give me?
The temperature?
Got temperature, what else?
Concentration of silver ions.
So I actually already know this one. So I know that the silver is 1.3 times 10 to the negative 4.
And then is it just the ratio?
And then we got to square it, yep. Okay, now I'm going to build a Rice chart just to connect it. But with solubilities, it's even simpler that if you can do it without the Rice chart, you don't have to. But I just want to build the connection from what we've learned so far. So once again, the reason why these ones get even easier, this doesn't matter because it's a solid, right? Don't have to worry about it at all. Okay, we know the value of Ag at equilibrium. The other thing that makes KSP Rice charts easier is the initial concentrations of our ions is going to be 0. Why do I have 0 of those when I start the reaction?
Because they're not there. They're just small.
Yeah, because what is the reaction? Dropping a solid into water, right? So these are always going to be 0. So the change that is happening here is, this one is increasing by that, which means the other one is increasing by half of that. Good. So we get 6.5, yeah?
Yeah.
Times 10 to the negative 5. Now, once again, I set up the race chart so we can make the connection. But literally, if I have this value, what's the connection between AG and CR?
Oh, it's a 2 to 1 ratio.
Yeah, it's just a 2 to 1. So you don't have to really build the race chart if you just go to the ratios and say, okay, well, if this is this one needs to be half the amount. Okay, so we're just plugging that 6.5 in times 10 to the negative 5 and plug it all in and we get a final answer of 1.1 times 10 to the negative 12.
The AG number on there, is that for the second power, the 1.3 e to the negative 4?
Do we square that, you mean?
Yeah.
Yes. So when I plugged it into my calculator, you got to make sure you square that value. Yeah. Okay. Questions on how we find that? Yeah, Connor.
So this one, so it's the same thing where 1 means it dissolves a lot.
Uh-huh.
Okay.
Okay, so building off Connor's question, you led me into my question perfectly. Turn to your table buddy and tell them, what does this mean?
So, for the
Yeah.
Tell your table buddy, what does it mean?
That's the rate of the
going in,
Several days.
shoot it fast.
Yeah, so it's saccharosis.
Okay, someone willing to share out loud, what does this, we gotta interpret our answers, right? What does this mean? What is this telling me about my reaction, about my solution?
Do we need to put on our units?
No, it's
There's
okay.
no
It's
units.
equilibrium, buddy.
Good question, you're trying to trick everybody. Because it doesn't have units, right?
Aha.
Don't trick us. Okay, what does this mean? So I'm at equilibrium, but what does this number tell me about my equilibrium, Eli?
Could it be that like that's the amount it can be at when it's put in, so like it can't dissolve at that point, or no?
Kind of. It's related to how much has dissolved. You are right there. So this tells us how much it's dissolving. So how much is this substance dissolving? Very little, right? This is a solution that we would say is a precipitant because you're going to have way more solid than you are dissolved, right? Things that are truly aqueous. So does anyone remember from our rules of the things that are always soluble? There was you're supposed to memorize a few of them. So potassium, good. Sodium, ammonium.
Wait, those are always soluble?
Sulfate.
Oh, close.
Sodium.
Another 8. Nitrate.
Nitrate.
So those 4 are always soluble, and the rule is with KSPs is in order to be always soluble is the KSP is actually greater than 1. Because if it's bigger than 1, what does that tell you?
It's at equal, well, no, at that one.
If a K is bigger than 1, what's favored?
Product.
Products, right? So if it's bigger than 1, that means it's all changing into ions, right? Yeah, Sam?
Is that the saturation point?
It's not like, so you can measure solubility. Solubility is like a measurement of grams per liter. This tells you the ratio of how much has dissolved. So they're connected, but it's not like, this isn't the measurement of how much we put in. Does that make sense?
That's not like when solubility hits, like that's like the rate it keeps, like constant rate it keeps going at.
So this is the ratio that is maintained when it's at equilibrium.
Okay.
So, okay, good. With your table buddy, solve this one for a smiley face. Ready, set, go.
I've already almost done the one. Okay, so that is, you know the value of OH in that.
Okay, saturation
The
value of
Saturated solution.
So that means that this should be half of that. One times and then except for 2 times
Because it says just in the
Going into
saturation.
So it goes zinc oxide goes into zinc oxide.
Okay.
Wait, what's the charge of zinc?
Okay, so this is your.
What's the charge of zinc always? So it's 1.
6,
2 plus
there.
2. Oh, wait, no. No, you? Okay, so you have, it's a 2-to-1 ratio.
You have 2 OHs? That's it?
Yeah, 2-to-1 ratio.
Once you have an answer, raise your hand and I'll come give you a smiley or tell you to try again.
Okay, we have an answer. Okay.
OH.
Okay, I have an answer.
You asked.
No, you have to spread it.
Hey, buddy.
9%.
You have to spread it outside. That's the,
Then you're closer.
Well, I mean,
I might have
I
said.
did that.
Yeah, I did.
That's not like all I need is
Minus 1.
I never.
Yes, I know. No, I did that today, and I have multiple
This
choices,
one.
so it's
Just kidding. Keep going, girls.
Is it?
and then
Yes,
this
there it is,
test
yeah.
is
Yeah,
if
I think I have that.
I apologize for my mistake. You should.
Look.
and then
I'm so rude. I'm gonna yell at chocolate.
Really close. I don't know if it's a
I'm gonna come to school with chocolate.
That's
And my
what I told
chocolate is gonna be cute.
Yeah, that's it.
it's like 4 times as long.
Yeah, we're gonna put
Oh, dude, I know, isn't that crazy though? Like, I don't know how I'm gonna stay for myself.
Maybe
Okay, so,
it's not
but you would,
power,
for the
it's
zinc, you would get more
it's
points.
holy.
Yeah, you do. You understand that,
I mean,
right?
the multiple
Do you like
choice
any
would
of
be
Oh,
those?
you forgot to cut this one.
Compared to,
Out of like
Like
these
these
O's
O's
right
right
there.
there, G is 2 and 1, so that should be half of that. But then that still has to be.
I know, right,
So
yeah.
yeah, you kind of have to do like 2 things with the ratio. You have to cut it in half or double it or something, but then also do the power side of it.
Oh, really?
If you think about it, 2 times
I guess there's also a clock on the wall. Like, they really imagine that it's like.
Good. Did you remember to square?
What's it called?
Yeah, it's just negative 6.
Oh, really? What you get on it? Oh. So you think it's
Yeah.
That's the answer. Yeah, so just capture the power.
Yeah, I do that, but then I never go back and look.
There it is. How's my face? Okay. Anyone understand or not get checked?
This is the class.
Okay. All right. Let's take a look at the next problem here, everybody. Still going on the same thing, but answering a different way. Now we're going to change what this question is asking. I found this question as a multiple choice question, but then I wanted to do it as a free response to keep it more open-brained. But I needed to change what it was asking because it's a little confusing how it's written. So change this with me. So what it says here is we're saying, okay, I'm taking some calcium hydroxide precipitates when 1 gram of calcium carbide is added. So it's saying if I pour 1 gram of this into water, I can make this substance. Okay? We want to know if I only use this much calcium carbide, is that enough to precipitate calcium hydroxide? So, or will it just be dissolved because we're not to equilibrium yet? Cross this question off. Right, the question is, will calcium hydroxide precipitate? Now, the first thing we need to understand here is they give us the KSP for calcium hydroxide. What is a KSP value?
The equilibrium.
The equilibrium for what? Solubility. So the first thing to not get confused with the solubility, this K has nothing to do with that reaction. What's the reaction that this K has to deal with? Just Ca dissolving. So the equation we really are looking at is this one.
So why did you give us the other equation? Trick us?
I don't like using the word trick, but
Teacher.
maybe. I mean, the idea is what they're saying is they're using this to make that, which then we're focused on here. So it's kind of excess information that doesn't. It does come into one part here. I guess you'll see where we use it, but besides that, that's it.
So are we doing this now in reverse? So instead of having CH2 plus and 2OH, we're going to have some acid
Kind of. What are we trying to find here?
if it will precipitate.
If it will precipitate. Okay? So what, in order for something to precipitate, we have to be to the point of equilibrium. So try to think of something we learned last time when a question said, how will the reaction proceed to get to equilibrium? What did we do? Say, Jordan. Q.
Oh.
I guess it wasn't last time, it was the time before that. My apologies. So the reaction quotient, if we look at Q and compare it to K, we can see how the reaction is going to proceed. And this is the same type of question. It's just precipitation is what we're focused on here. So what is Q? It's the reaction quotient, but what is it? It's the same setup, right? So Q is just Ca2 plus OH minus squared, just not at equilibrium, or maybe we are, we just don't know yet. Okay? So we need to find the values of these at the moment we're at so we can compare it to our K. So we know the grams.
And then we just have to do that grams of that and the grams of OH.
Good. So we got to go from grams of calcium carbide all the way to moles of our ions.
Oh.
Okay?
Oh.
So I'm going to go from grams of calcium carbide to mole of calcium carbide.
Don't bring this back.
What number do I use?
The more
The molar mass, which they gave you, 64. That was nice.
So nice.
Oh, that's a nice number.
It's a very nice number. That's why it's a multiple choice question. It's because normally you wouldn't have a calculator to solve this. So, okay, so then for every 1 mole of calcium carbide that reacts,
We have 1 mole.
1 mole of calcium hydroxide reacts.
So it's just going to be.
Now, once again, I know this does nothing mathematically, but it's important to think through that mole ratio. What did I write? I forgot to write mole. Okay, my parentheses looked really big. Okay. Now, I want to actually get to the ion of calcium hydroxide, right? Now, once again, it does nothing, but I want you to think through it here. Sorry, it's getting a little squished. For every 1 mole of calcium hydroxide that I have, how many moles of calcium ions are made? Just 1, yeah, because it's a 1 to 1 ratio. Plug all that in. get what? 1 times 10 to the negative 4?
Like 64 divided by 64 is 0.01.
So 1 times 10 to the negative 4 or 0.001, however you want to write it. Which one do you like better? Scientific notation or no scientific?
Well,
Not
I
scientific.
see it better.
Okay, so 0.001 moles of calcium ions. Questions on how we got this number?
Why did you have to get to that number?
Because we need to plug it into here, because this is what we're trying to solve in the end. So we needed to find this to get there.
So then we would find
Thank you.
that.
Does that make sense?
by the-
Yeah, no, good clarification, Sam. Okay, so now I can plug this in for calcium.
Oh my gosh.
Oh, that wasn't really.
He had not done yet.
And we
And then do we just
divide
take
it
8
by
times
those.
8 divided by
It's a 2.
No, never mind.
Yep, so now we just do the ratio. So hydroxide is twice the amount.
0.002,
So 0.002, that needs to be squared though.
which is
Okay, so then in the end we get 4. Oh, because that's getting cubed or squared. So 0.0.
Times 10 to negative.
Oh,
I was gonna say, I'm gonna use that scientific
Oh,
notation now.
times 10 to the negative nine.
oh, you don't.
No, she put that right. Yep, I'm so
Oh, I know there's a way that you can like just calculate like counting all the.
Yeah, you just count up all the decimal moves, right? Okay, so now this is our Q. It is less than the KSP. So don't say it out loud, but decide in your head, does that mean that we are going to precipitate or we're not going to precipitate? Think for a second. Are we going to precipitate or are we not going to precipitate? What's the actual answer to the question? Because this would give you no points. I know.
Don't say no.
Okay, give me thumbs up if you think yes precipitant, thumbs down if you think no precipitant. I like the faces some of you give me when you give me answers. You're like, maybe. There's not going to be a precipitant.
Because.
So, think back to last time, or 2 times ago, if Q is less than K, which way is the reaction proceeding?
To the, there was no the products.
To the products. Are the products the precipitant?
No.
So since we're shifting to the products, those aren't the precipitants, so the answer is nope, we won't get any precipitant.
Why is Q less than K? Is that just
Yeah, I know,
always?
I held that for sure.
No, so this was Q, K is the given.
Oh.
So you just compare what you found to what was given.
You
So
have a 50% chance of getting this problem right.
true,
Dude, that'd be awesome.
true.
You can say no.
I'm guessing that most likely would be like justify your answer, but okay, questions on that? Okay, the last thing we didn't get to, just to kind of get you thinking, is just a way that Le Chatelier's affects the solubility. So we'll just talk about that last section because we have like 2 minutes left of class next time.
Okay.
Okay?
That was 7.5.
So that does mean